The last half of part 5 talks about how we deal with continuous random variables. So this is different than our discrete, right? Discrete, we can actually write out all the possible values, whereas with continuous, we can't. There's actually an infinite number of possible values that our random variable can take. So we need something a little bit different, and we're going to be using a function as opposed to a table or list of probabilities. So our probability density function, which is how we represent this, is going to be literally a curve. So you can think of this as like some curve where we have some probability of the outcome and the outcomes on our x-axis. And we'll have some curve where for certain values of x it might be higher, certain values of x might be lower. But there are some requirements for this. This whole area under the curve has to be 100% or 1. That's the entire probability of the entire sample space. And then each and every one of these actual heights has to then, of course, be less than 1 and between 0 and 1, right? But the issue here, and a good thing to notice, this is actually not the probability. Sometimes we'll label it that way. This is a function. The actual values at any particular x, this is the probability of any particular value is actually 0. Because if you think about this in terms of our, classical probability approach, we're basically saying how many values do we care about, 1, out of how many possibilities, and as we were saying, there's infinite. And so those of you taking calculus and dealt with limits, basically this is approaching 0. So this is approximately 0 for any one of these, regardless of what this height is. So the height here of this probability function doesn't actually mean the probability at a particular value, which is sometimes hard for students to sort of get their heads around. All right, so here's an example. We got 2 that are going to help us out. A random number generator will select any number between 0 and 1, not restricted to integers, with equal likelihood. Find the probability that x is between these different values. So again, the only way that we could actually write this out, because we can't write every possible value, is using a curve. So we just said our x's are between 0 and 1. And we also have this idea that they're equally likely, right? Equal likelihood. So whatever our curve is, it's a straight curve. It's not higher at any value than it is in another. And then it drops to, oops, whoa, that was intense. It drops to 0 outside of this range. So this is our curve. Not much of a curve, but that's what it is. Now, the actual height of this, again, doesn't necessarily mean anything, but we can figure that out because we do know that the entire area under here, this whole area, has to equal 1, right? And if that area is equal to 1, well, we can figure out a little bit more because we know how to find the area of a rectangle, right? Area of a rectangle is just base times height or length times width, however you want to think about it. Our length here is 1, which means our height, if this area has to be 1, our height is just 1 as well. So this must be at 1. And then there's a number of ways to do these next problems. So the first one here says, what is the probability that we're between 0 and 0.8? So 0.8 will be about there. And whenever we're talking about probabilities for these continuous ones, we're talking about areas under the curve. So those of you who have taken calculus, we're really thinking about integration. So in this case, we're integrating a constant from 0 to 8. But don't worry about that. We don't expect any calculus knowledge in this class. All you need to be able to do is figure out an area. But we just figured out the height of this thing is 1, and we can figure out the base is 0.8. You can also think about this instead of an area as the proportion of the curve. So if this is our whole curve, what percent of our curve did we just shade? So either way, we're going to get 80% here. And of course, you can keep doing this for all the different values that are here, right? The next one says we want the area between 0.2 and 0.5. So 0.2, 0.5, bloop. Again, we could think of this as a proportion. So I shaded, what, 0.3 of the whole 1. Or we can think of this as an area. The base times our height, 0.3 times 1. This is 30%. And then the last one is a trick question. I think I have some of these on the knowledge check. I can't really remember. This one says exactly equal to 0.5. So if we wanted to write these in notation, by the way, our random variable is an x, so we could do this. Oops. I want to use the same color and not add extra decimals that don't exist. This last one says the probability that our outcome is exactly equal to 0.5. And as we said, you can't have an area if we're just talking about a line. So this would be approximately 0. Doesn't matter that the height of this thing is 1. That would be crazy, right? So another thing that I want to point out is in the binomial section, it really mattered whether or not we put equal signs or not, because that included a whole nother outcome and usually made a very big difference in terms of our probability. But in continuous land, since each value is approximately 0 probability, whether you include or don't include an equal sign doesn't matter. So we actually get to be a lot lazier when we read our word problems in the second section of part 5, because we're sitting there going, okay, it says at least, but all I need to know is at least is greater than, not greater than or equal to, whereas in the binomial section we had to be a lot more nitpicky.